This is project 2, video number 3, the one in which I do the documentation and finishing touches. First thing I want to talk about, I said I wanted to do some more checks on this, and I got a good one, I think. I investigated the escape velocity. The idea is, with a case of an attractive force, if this thing starts out with a relatively small velocity, then it's going to slow down, come to rest, and then come back. And we were actually asked to find out where it came to rest and how long it took to get there. If you give it a big enough velocity, it's going to slow down on the way up, but eventually it gets so far away from the negatively charged particle that there's essentially no force on it, a negligible force on it. And if it's still got some velocity by that time, it keeps on going at a constant velocity, whatever that final velocity is. And then in between those two situations, if you give it just the right velocity, it's slowing down, but by the time it gets to a distance so far away that the force is negligible, it has slowed down to a speed of 0. So it's in between keeping on going and coming back, essentially gets out there and comes to rest. It's you can think of it as a theoretical situation, but it's a cutoff between coming back and keeping on going. So I'm going to find the velocity that makes that the case by saying, in the before picture I got the particle with some initial velocity, and that's what I want to find out for the charged particles and the mass of this one, how far apart they start out. What is the velocity I have to give it so that I'm at that in-between situation, that boundary state between coming back and keeping on going. So in the after picture I say it's out there an infinite distance away, but it's got 0 velocity. It's just slowed down to 0 as it arrived an infinite distance away. So that's my after picture. Apply conservation of energy. The potential in the final picture is 0. Potential energy is 0, as is the kinetic energy. And in the before picture I got the charge of this moving particle, QB, times the potential it's in, which is the electric potential due to the fixed particle, QA. And go ahead and solve that for V0. I get this expression. And then I use the example that I was playing around with when I was doing the programming. In other words, what I was using to test the program to see if it seemed to be working properly. And I couldn't tell for sure. It seemed to be working all right, but couldn't tell for sure. Found out it was kind of cool what happened if you launched it greater than the escape velocity. You get a negative distance and an imaginary time. So that's your clue. Get a negative distance and you know that it never comes back. And then it worked if I launched it at a slow enough velocity. So I went ahead and plugged in the values that I was using for my test case, and calculated the escape velocity, which is 10.94836. So presumably the closer I get to that velocity without getting right up to it, the longer it should take to come back. So it's should be getting farther and farther before it slows down to 0. And I had actually found that after I turned off the video recording device. I played around with it some more and found that that number experimentally, and that gives me every confidence that it's working. So I found the number experimentally using the program. Look at that, it takes 100,000 seconds to come back as we get really close to that 10.9483 is what I found there, and 10.94836. It'd be interesting if I've definitely rounded there, stopped writing down digits, so if it goes over, if I put a 6 at the end of that. So I'm going to go ahead and do that. One more digit. And that's roughly exactly, it is the escape velocity to 2, 4, 5, 7 digits. And this thing says, yep, it does take a long time to come back. And presumably if I go over that, and I put a 7 instead of a 6, for instance, it never comes back, and sure enough, I get an imaginary time and a negative distance. So now I'm really confident that my code is working correctly, as it has the correct behavior right around the escape velocity. So I'll pick a number that works again. That was 3.6. So that's 7 million seconds. And it goes a distance of about 45 kilometers. That's, 45,000 meters. So 45 kilometers. But going very slowly by the time it gets way out there. Because you can tell because it takes so long to get out there. Alright, so now let's actually do the documentation. So in this function description, I choose to copy this. I'll copy the function statement itself, and then say here you, the student, have to describe the situation and say what the function does. In that statement, you should tell the user that QA and QB have to have opposite signs. One's positive, one's negative. So describe the situation. So that I think that will naturally come up in your description of the situation. And then tell the reader what the input variables are. You can call them the arguments to the function, or argument variables. I'm going to call them input variables. They're probably more often in other contexts referred to as arguments, but it's these variables right here. Alright, provide a list, so explain what each one is. So I'm actually okay, probably with the function statement. You don't necessarily have to do this. I think I'll and given that I put that up there, I don't think I really need that statement at the top that says function, so I'm going to get rid of that comment. I changed my mind. Percent output variables. And then I think it's nice the reader of your function description sees there, and gotta do same thing. So say provide a list. In a sense, the list is right up here, but what I mean is say RF, and then say what RF does. So R percent go RF, and then say what RF does, or is here, what it represents. It is the greatest distance achieved by the particle. Mention that if RF is assigned a negative variable, comes back negative, I think I'll call it. So they gave it too high an initial speed, and it never returns. And then percent $t, say what that one is. It's the time that it takes to get to the maximum distance that it achieves. Assuming that that it does eventually come back, and you can mention it if you want. I think you're already covered. If RF turns out to be negative, then T is going to be a complex value. It's going to have an imaginary part, and you can tell the reader that. I don't think you have to. You say who it's by. So your name has to be in the function, and I want to save this. And here's the thing: if somebody doesn't have access to the code, but you saved it saved your function in a library, for instance, so that they can run it, and then somebody wants to use your function, but they're not sure how, what they can do is type in help and then the function name. And presumably that description that I just typed in comes back. So if you set this up right, so the first line of your function is this function statement. It's really going to be the first one that's executed, but I mean if you don't put any comments above that, then the first comment after that and all the contiguous ones, I get a bunch of comment lines, but it's one right after another with no coding in between. They become part of the help library. In other words, they are shown when somebody types in help and the function name, your function name, at the command line. So hopefully you use a little creativity and you don't come up with the same function name that I did, get dist in time. I mean, you don't just use the same one that I did, but whatever your function name is, they type in help, your function name, and they should get a description of what the function does. So you should be telling them, we have a fixed charge and a moving charge, a fixed charge QA and a moving charge QB, or a charge particle that's fixed in space, that's QA, and a charge particle that's moving, that's QB. The moving particle has mass m, starts out with velocity v0 directly away from the fixed particle at a distance r0 from the fixed particle, and you say what the function does. So the idea is somebody reads this and they know exactly how to use your function. They know what it does and they know how to use it. Typically, when I want to use a function somebody else wrote, this list of the variables is really the most important part. I guess they're all important. I get the gist of what the function does by reading the description, but then I find out exactly how to use it, what I have to type in order to be able to use it by reading the description of the input and output variables. Alright, I do remember that we have to give attribution. And, say what resources are used. Alright, the code. Resources outside of MATLAB itself. So if you use the help function within MATLAB, you don't have to write about that. But generally, if I want help with some MATLAB idea, I'll go to the internet and type in, Google MATLAB space, and then whatever the idea is, like array, for instance, if I want more information about arrays. Alright, let's see if we can see if anything doesn't make sense to the user to find after getting the max distance separation achieved by particle B from A, I divide the line segment from initial position to final position into this many evenly spaced segments. I think I'm going to say number of points of evenly spaced points from initial position to farthest position. So I think if you do a good description, I know what you mean by the farthest position because you've already mentioned it. So I'm going to put a % there to make that into a comment. Then that's the Coulomb constant. People should be able to know that. This is RF. I've set above what RF does as a return variable. Array. Now that they know what R0 is, that was an input variable, this was an output variable. I think I just said it was an input variable, but it's an output variable. And I said what that is. People who know MATLAB should be able to figure out what's going on there. This V array, I think I'll put that now find velocity of B at each point in each position. I think I'll call it each position in R array. So the idea here is for things that aren't obvious to the user, you should explain what's going on. I call this distance between points. Here's the time each T array element is the time it takes to get to a point from the previous point. To a position, I think I'll call it. And then I'm going to make that a comment. Control X, delete. I think I prefer to put that after I just calculated the T-arrays. Alrighty. And then total time. Total time for B to get, it's particle B, so I should probably be calling it particle B all every place. To get to farthest position from A, if you like. Okay, then under the attribution, make sure you're not just copying what I wrote here, but state, I used video 1 to, I figured out all the pencil and paper part on my own, and I used video 1 just to check my work, or, however that actually went. I want the attribution to tell a little bit of a story. So tell a story here about, what help you got to get this. I'm interested in what you were able to do on your own. This is the second one, so I'm sure you're starting to pick up some of this MATLAB stuff. Okay, I think I want to save it. Run it one more time. Well, maybe not just one more time, but run it again to make sure I didn't mess it up. And I did mess it up. Forgot to put the percentage sign in there to tell the program that it's just a comment. So let's try that again. And now it's working again. Let's make sure that if I put a semicolon afterwards, that nothing gets printed to the screen. So there's the command, and then the next line with nothing printed out. It is interesting, MATLAB's got this little feature to it that tells you. So for instance, if I started out at a smaller separation, make that a 2, oops, I'm going to go this way, and then 2, started out at a smaller separation. So even though it doesn't get printed to the screen, I can see in my workspace that these values change. Let's try it. Yeah, sure enough, they get a lot smaller. I made it so that it started out closer, so you would need a greater velocity, greater initial velocity to make it, be close to the escape velocity, and make it take a long time to get out there and for it to go a long distance. Here it's only going 6 centimeters. To the position 6 centimeters away from the other charged particle. Alright, now we gotta check and make sure I got everything covered. So make sure if the user enters help your function name, I check that out. I got it working, although admittedly I haven't really written the description of the function. I want you to do that in your own words. So pencil and paper part, it's got to have complete algebraic solution. I had that with diagrams for each function, outline the steps, and you get that. It's also a good idea to do something to check to make sure it works. I'm not going to require that you guys have the check that I showed you at the beginning of this video itself, but you should recognize that's a good idea. Like you want to prove to yourself that it's actually working, which is all I did on that. As for the program part, reasonable attempt at writing it. One or more .m files. I got one .m file. Whether it works properly, I've convinced myself that it works properly. And then I checked that business out with the semicolon to make sure that nothing got printed to the screen. That was perfect. 1 point for documentation and final touches. That's what this one was actually about. I remember typing my name in there, so I got that covered. Documented comment starting on the first line saying what the function does. Another set of comments providing a list of the arguments. I didn't really do these things all the way through, but I put a placeholder there indicating that you have to do them, so make sure that you do them, and discussed how to do them. List of the return variables, state what each one is. So not just the name of it, but describe what it is, explain what it is, tell the reader what they need to know to make sense of it. For the case of a function that includes segments, statements that are not self-explanatory, I thought in this case some of them were not self-explanatory. My T array, for instance, I thought that needed some work. So explain what those are. I think I got you started on those comments. I'm not sure that I really... I wanted to give you the idea what you have to write there for those as opposed to writing it for you. So make sure you explain what various pieces of the program are doing when it's not obvious to anybody who already knows MATLAB. So for the case of a function that produces one or more graphs, we didn't have that. No graphs. You must provide attribution. Okay, I got that. Comment, what resources. So I mentioned that you actually are the one that has to do that. If you're watching a video, make sure you provide your attribution in your own words. Make sure it's not identical to mine. It wouldn't make any sense for it to be identical to mine. So your attribution should tell a little story, about how you got to having a finished project. What you had to lean on, what you needed help with, and hopefully what you need to lean on. You get to the point where all you were doing was checking my videos to make sure that you had stuff right, and to prove that it was, or to make sure that it was okay. All right, I think I'll take one more look at it. I don't know if I can make this a little bit bigger. Number of evenly spaced points. This one goes a little bit beyond the line. This one comment, but I think it's okay. Kind of comes off the page. I think if you want to fix that up, you can just put percentage in front of it. Number of evenly spaced points from the initial position to the farthest position. And I got this one overruns itself too. Goes over the borderline. So if somebody prints this out, it'll be hard for them to read if you don't make sure it doesn't run past this extra line over here. So then this time it might actually be one last time. I think I'll try it a couple of times, but does nothing. Did not change. Oh, there it is. So at least I can see those values. I want to go with 3 there, and then these values get very, very big. So seems to be working. Obviously you can do this with any charge. So if I double the charge of one of these, it's not going to get nearly as far away. Just playing around with it a little bit. It's not going to get as far away. My instincts say not nearly as far away. Yeah, that's the same value I got when I changed what was it, the initial separation. I think that they look awfully familiar. So if I made that a 1.5, so here a little bit further, so 0.06 changes to 0.09. So yeah, it's working. I think that does it for Project 2, video number 3, the documentation and finishing touches video.